I think what I'll do now is quickly introduce the 3 locations that we're going to be going to. So we've got Josh Wilhite, who's at what we call the Ross Brow, which is the area right where the cage lets out at the 4850 level. We've got Mike Fath in the Century Utility Cavern. So that's that's the still enormous but slightly smaller cavern that holds all the utilities. And then Jolie Macier is in the South Cavern, one of these 2 enormous caverns that are going to house these huge detectors. So I think with that quick intro, I will throw it over to Josh to pick up the story from here.
Thank you very much, Steve. Can you hear me all right up there?
Yep, we hear you good.
Excellent. So as Steve mentioned, I'm Josh Wilhite. I am the project manager responsible for building out the infrastructure that will support the detectors down here at the 4850 level. And I'm standing at the Ross Brow area. So why do we call it a brow? You can kind of picture your forehead turns towards your eyeball. That's your eyebrow. Same principle here. We've got the Ross shaft right behind me here. This is where the shaft goes from vertical to coming out into the drift, which is a tunnel that never comes out to surface underground. This is a very critical part of our infrastructure. Every piece of material that gets delivered to the 4850 level has to go through this shaft. And that includes the beams that form this cryostat that contains the detectors. And some of you may have came from Rapid City. If you happen to go over near the School of Mines, there's a warehouse there that's got all of the beams that were fabricated in Europe and shipped across the ocean to us here, just waiting for the opportunity to come underground. Some of those beams are 45 feet long, and they are a little over 3 feet deep and about 1.5 feet wide. There's some examples around. If I'm not sure what's available to be seen today during Neutrino Day, but those 45-foot long beams, you have to get those underground, and the shaft is relatively small. So the cage or elevator car that you ride down here is about 5 feet wide, 12 feet long, and about 12 feet tall. We are building one that's taller, but we're not building one that can handle a 45-foot long beam. So you actually have to hang that beam, dangle it down the shaft, and then rotate it into the level here. And so that's why this is the last bit of excavation that we did. And you got to get closer so that the camera adjusts. You can kind of see the top of it there. That is about 60 feet above the floor level, just so that we can get those 45-foot long beams out of the shaft and delivered underground here. So this is obviously the lifeblood of the project. We're pretty proud of this particular area. This, as I've mentioned, is the last thing that we excavated in preparation for the next phase, which is the infrastructure we're building out now. And I've got some kind of neat show and tell things down here at the station right now that give you a little bit of a feel for the types of things that go on. So we've had a bunch of equipment down here that we've been using to assemble some steel. You'll see Mike Taft show some of that steel here a little bit. One of which is a mobile crane. And, you know, a mobile crane doesn't fit in a 5-foot by 12-foot cage. So you have to take it apart. So I've actually got one here that we're done with. And we just went through the process of disassembling this. Hopefully people can see that. And so this is the chassis, this is the frame. So you can see we took the wheels off, we took the cabs off, we took the boom off for the crane. And this piece today actually will be slung or hung underneath the cage and brought up to the surface. Some other interesting things that we have here at the station. Got a small forklift behind me here, and I've got a big telehandler. And so that telehandler, you can tell I'm 6'2". A telehandler does not fit in the shaft either. And so same process. We had to take the boom off, we had to take the wheels off, take it completely apart. We like to say that you're only limited by the tires. It's really hard to weld tires back together and get them to hold air. And so you can get the biggest piece of equipment is kind of limited by the tires. Something else that I can show you from this location, hopefully, is up above me in the distance a little bit, is some of the infrastructure we're putting in. So there, if you can see it, there's a little orange pipe kind of in the center of the ceiling, or back as we call it. That's actually part of our fire detection system, smoke detection. So That's pretty critical underground also. We don't have a whole lot of things that can burn, but boy, if they do, it's a really bad day. You got to get everybody out. You want to know that as quickly as possible. And so we have these tubes that continually pull air in and test that air for smoke so that we know as soon as we possibly can. And then the black pipes that are going across the tunnel, the drift, those are the sprinklers. And so obviously if there's a fire, we want to be able to put it out. And so we've got a full sprinkler system. And we've got some of the supply lines that go along with that. The lights you see, these rope lights, those are not permanent lights. Those are a temporary light that we use to facilitate construction. They work really well, but that's another part of the infrastructure that we will be installing is permanent lights all the way around here. So I think that's probably enough for right now for this area. So I'm going to throw it over to Mike Pfaff to carry on the conversation in the Central Utility Cavern. Mike?
Thank you, Josh. Hi, everybody. I'm Mike Pfaff, a services manager for the fire detectors and cryogenics project, which follows with Josh as we continue on with the installation. Kind of to continue on a little bit with what Josh was talking about with utilities and installations. You can see here in this cavern in the CUC, the red fire suppression and the black fire suppression piping that he mentioned, the smoke detection. You can also see a lot of steel structure here at the end of the cavern. This steel structure will house the electrical substation distribution systems for underground. It's also going to all of our working capabilities. That'll be the consolidation point before the cables run up the shaft into the surface. Additional to that, we'll have once it's all finished and we're up and running for operations, a small control room and a multi-purpose space, a underground headquarters, if you will, for the operations of the detectors. So we appreciate all the work that Josh and his team are doing to get all this ready and continue to move us forward. Along with all that, you can see a lot of these hangers from the ceiling. All the utilities infrastructure will be secured to those, routed up out of the way, giving us space to work on the floor. You can see here a lot of the duct work for air handling here along the side here that's getting ready to be installed with all these lovely scissor lifts and boom lifts that, as Josh mentioned, all had to come down that same shaft, be disassembled and reassembled down here to be able to do our work. Turning and we go down to the opposite end of the cavern here, we have the spaces where our nitrogen generation and cooling system will be housed, which helps us cool down the argon at the very far end. And then closer to us here, nearer to myself in this location here, the argon filtering and the argon cooling for the detectors will be housed. One interesting point made here, you heard Steve talk about the beam line that's going to be coming all the way out here from Batavia. This point in the floor right here is the target with which that's all going to be sent here to us in South Dakota from Batavia. So some very interesting details here in this cavern. It is by far the farthest advanced insofar as the infrastructure installation that's going on here. And so I think that's probably a good portion of what's happening here. And I appreciate the work that Josh and his team are doing. I'd like to invite Jolie Mace here, who's also underground with us, to maybe tell you a little bit more about our other caverns.
Thank you, Michael, and to Josh. And yes, indeed, we are in the detector cavern. And in fact, I'm not at the 4850 level. I'm at the 4910 level. And that's the distance between the space where you saw the other folks and the depth of this cavern. And so indeed, we will build very, very large detectors here. And we will start with, in this particular cavern, with the 6 million pounds of steel, structural steel, that are waiting for us in Rapid City. And we will use about 1,000 loads down that shaft to get that steel in place here and build a very large structure. And once we've done that, we will start to assemble detector components inside that very large box. Steve mentioned earlier that it will hold 17,000 tons of liquid argon. In case you're not thinking about tonnage, that's 3.5 million, equates to 3.5 million gallons of water. So very, very large, 6-story high structure. And the entire cavern, in fact, is about 5 basketball courts long. So very expansive space. So I'm standing down in the middle of that space between where we would put 2 of our detectors. And right now, across the world, we have people in more than 30 countries building components for those detectors. And once those cryostats, those very large cryostats are assembled, we will start to install those detector components as well. And teams from around the world will come here and help us with that work as well. So the entire cavern, as you can see, is about 31,000 square feet and very tall. So we're very excited for the opportunity here and to assemble folks and build these very critical neutrino detectors to help us unravel the mysteries that yet remain for neutrino physics.
Great, thanks a lot, Jolie. Jolie, could you give us a wave? Because I think there's if we can put up the cavern shot again. Think about, can you see, just to give you a sense of the scale. These things are monumental, and this is only one of them. There's another identical one to the north as well.
All right. Any questions in the room for those underground?
Okay, Wyoming, with Bill Gates and Warren Buffett are building massive, we're spending billions of dollars in sodium reactors, modular. Does this neutrino technology, you mentioned the word nuclear at one time, is there any indication that it will be involved in that construction and that research?
So neutrinos are produced as a byproduct of nuclear reactors of all different types. There are various types. The one you mentioned, usually they're distinguished by how they're cooled. So the liquid sodium is actually a very efficient way of cooling, but there are also other cooling methods. But all of them, in the process of releasing energy when there's the fission of the fuel, that process also releases neutrinos. And so I would say that they're really a sort of a byproduct of the nuclear technology, but a very interesting byproduct, because although it's hard to detect them, you can detect them. And there are colleagues of ours who are working on methods to detect, well, and we have detected neutrinos from reactors. And in fact, there are interesting things you can do detecting neutrinos from reactors, particularly if you're worried about what that reactor is doing. If that reactor is perhaps not there for energy generation, but perhaps it's there for other reasons, there are characteristic signatures in the neutrinos that come out that let you tell the difference. And so there are people who are colleagues of ours who are working on detecting neutrinos to better understand, is that reactor really there for research or for power, or is it there for some more maybe nefarious purposes? So that's the quick reacting neutrinos story.
Next question in the room here.
Maybe we're not there yet in the presentation, but you mentioned there's going to be a facility in Chicago that's going to direct neutrinos here. Is that correct?
Yeah.
So if they're a very prevalent particle in the universe, is there a signature or something? How do you know they're coming from there? And how is the argon gas not just catching random ones that are coming through here already?
Excellent, both excellent questions. And actually that leads me into explain, which I didn't, why all this is happening at 4850 feet underground, which is a question that needs an answer. So let me answer that first, then I'll come to the beam. So those enormous detectors, not only do they detect neutrinos, but they can detect a variety of other particles as well. In particular, there's a constant rain of particles from the cosmos coming down on us. We call them cosmic rays. And many of these sorts of experiments, we like to move underground so that we can shield out all of those cosmic rays and really focus on the interactions that we're interested in. And so that's the reason why we're deep underground. The other part of your question, I think, was if they're so hard to detect, how do you know that you're aiming the beam right, or something?
Those versus something else.
Right. So excellent question. So aiming the beam is a constant worry for us, and we're very confident we'll do it right. The way that you can really know that you've aimed the beam right, the beam from Chicago is not a continuous beam, it's pulsed. Very short pulses, about 10 microseconds. So you know, and we, through GPS technology, we know when to expect the beam. So I've worked on a number of neutrino experiments, and one of the most exciting times is when you first turn on the beam. Like, how do you know what you're seeing is neutrinos? The way that you know is by making a time plot of when the interaction occurred compared to when you would expect it to occur from the beam. And so you see a big bump when you expect the event to occur from the beam, and that's when you know that what you're seeing is neutrinos from the beam, and you've got everything else timed in correctly. And that's what we'll do in this case as well.
Very good. Other questions? Was this a question here? Yes, we have a young question.
How do they get the water source to put out fires?
The water for the fire suppression.
All right, I can take that one. So that's a great question. It is a challenge when you're working a mile underground to manage water. So we have natural water that's rainwater. That big open cut, when you look out the window, that is a giant funnel. And at the bottom of that funnel are holes that come into the underground here. So we have to manage that. But we also need water to do fire suppression and cooling and all kinds of different things. And we can't bring it down all at once because the pressure would be much, much too high. It's like a submarine. The deeper you go, the more pressure you have. And so we actually bring it down through pipes in this shaft that's right behind me. And we go down in stages. So we'll go down several hundred feet. We'll come out of the shaft into a tank. That relieves the pressure. And then we'll go down again and into another tank all the way down to the bottom. And that's, in fact, the same way that we get water back up from the underground is we pump up in 1,250-foot lifts. And so we've got pumps every 1,250 feet all the way up to avoid having to put in very, very thick pipe and very, very powerful pumps. Not that the pipe isn't already thick and the pumps aren't powerful, but boy, they'd be a lot more powerful if we had to go all at one go.
Very good. Great question. Other great questions. One at the back. Steve, we'll get that.
I have three questions. The first one is, do you know what frequency they are? Do they have color? And how do they communicate with each other?
The neutrinos in particular. So, okay. So the neutrinos interact through only one of the forces that we currently understand govern interactions between particles. So we're most familiar with electromagnetism, which is what is basically forms the world around us, essentially. There's also the strong force that binds particles together into nuclei. Neutrinos don't interact via either of those. They interact by a third, what we call weak force, because it's very weak. And that's the reason why they're so hard to detect. So it's this weak force is what binds them together. They come in three flavors, three types. You might say three colors. That's sort of an analogy with color, and there isn't really a direct physical connection. And what we're interested in doing in DUNE is understanding how those types transform into each other. It's a piece of sort of very fundamental quantum mechanics. By understanding that, we can understand what the neutrino masses are, strictly the mass differences, but we can understand the mass and how they mix, how they're related to each other. So there are things which are all analogies, direct analogies with things like color and interaction relationships. But we think about them in sort of very kind of strict physicist terms. But they're all analogies to the things that you mentioned. Frequency for us is sort of equivalent to energy. And so that's really the energy with which you emit the neutrinos. that has corresponds to them having a particular frequency.
Frequency that they're vibrating on, or is it?
No, if given if you give it a different energy, the higher the energy you give it, the higher the frequency of the interaction. We're now really talking about quantum mechanics and what's really deep down in there. Okay.
So Steve, if I could jump in a little bit, not quite frequency, but I think this is an opportunity perhaps to explain why we are the distance we are from Fermilab and the oscillation. I don't think you described that before.
Yeah, you want to go for it, Josh?
No, you're the physicist.
Nice try.
So I'll explain some engineering later, and you can. Yes, that's another excellent point. Like we're 1,300 kilometers from Chicago, the origin of being. Why that far away? And it has to do with how those neutrinos transform from one into the other. It takes they oscillate, they transform sort of back and forth with a particular wavelength, with a particular frequency. And so by going 1,300 kilometers away, it turns out, given the other properties that neutrinos have, that's an optimal distance to measure how many neutrinos have transformed from one type into another. So that's basically why we chose Fermilab and SURF to be the start and end points of these experiments, is to have that distance. I think there was a question there.
Then I have another one up here.
Hey, good morning. I was just wondering, was argon chosen because it was like the best gas to detect, or also because it's like one of the safer gases to store and deal with? Like, would there have been better gases that were just possibly more dangerous to work with?
I feel like I'm hogging.
Steve, do you want me to?
Yeah, why don't you take that, Julie?
Yeah, I'll start and then you can fill in any blanks about other neutrino experiments that have used argon. So of the media, in fact, argon is not the best. However, physicists would love to use xenon, but it's very, very, very expensive. And so argon, the neutrinos do interact beautifully in liquid argon. And so in fact, what we didn't talk about is we're going to get argon delivered as a liquid, and then we're going to gasify it, and then bring it down the shaft, and then re-liquefy it actually in the cavern where you saw Mike earlier, in that central utility cavern. So yes, we've done a ton of prototyping of these particular detectors, and the events that physicists see in the liquid argon are beautiful. And I guess Steve can comment on that more.
I'll just add a couple of things. So neutrinos don't interact often, but they do interact with everything. So it's not a question of what neutrinos interact with or don't. It's a question of how easily you can see that interaction. Given that you need something like 17,000 tons, whatever it is, it better be pretty cheap. And that immediately limits you down to a list of 4 or 5 materials, right? Water is one. Turns out liquid argon. Liquid argon is quite cheap because argon is used in welding, and it's a byproduct of extracting oxygen from the atmosphere. So, and then the other nice property that argon has, the way that we detect these interactions is that the interactions release a lot of electrons from the surrounding atoms, and we can pull those electrons out with an electric field, detect them, and a little bit like how a digital camera works, we can then infer a 3D image of the interaction and the particles that came off it. Now, in order to drift those electrons by many meters, you need something like argon, which doesn't interfere with that drift and also can be made very pure. Water, for instance, would snap up those electrons very quickly, and it wouldn't work that way. So it's sort of price and inertness. The fact that it is completely inert it's connected to the electron drift, but it's sort of an added bonus as well.
One last comment on argon versus xenon as I go to another question here. Argon in the atmosphere, 1%, 1 part per 100. Xenon, 1 part per 10 million. So there's a quantitative comparison. We do use xenon to measure dark matter at SURF. The LZ experiment throws cost out the window and we helped arrange $10 million to purchase xenon for a 10-ton instrument that's underground right now, the most sensitive dark matter experiment in the world. Not 17,500 tons of anything, but decent quantity nonetheless. Next question here.
Two-part question. One is, once you all start taking those loads of beams and other materials down, how long will it take to get all of the beams and other materials down there? And then once you've got the materials down there, how long will it take to build both of the cryostats?
I think pretty much
So-
any three. Yeah, Jeremy, do you want to take it?
Sure.
I think Mike should
Yeah.
take.
Yeah, actually, Mike, let's give Mike a turn.
Sure, thanks, Steve. So insofar as the immediate term, so the steel for the cryostat structures takes between 14 to 18 months to bring all the steel pieces down. Each cryostat has over 2,200 individual pieces. And then beyond that, we have the cold insulation that lines the internal part of that steel structure, and then a stainless steel membrane that goes inside that before we start installing the detector components that Jolie had mentioned. So overall, we anticipate and expect that we will have about 3.5 to 4 years worth of continuous material movement down the shaft from the inception of material moving till we wrap up the installation, at which point we will have had about a year's worth of argon gas deliveries, and then probably another 18 months or so of argon gas beyond. So overall, about 5.5 years of material deliveries, all of which probably, based upon our estimates, are about 3 or 4 trucks a day. So really, it's not much in the line of truck traffic for deliveries, which is great. It's just a very long duration.
For science in 2029. So with all that work, we will be getting science in this decade. Maybe go for that one first and then over here. Yep, go for it. Yep.
So I wonder, why did you guys choose this cave? Why didn't you guys choose like another cave to do this?
It's an excellent question. Josh, that's I don't know. We don't have a geologist on hand. You're the
Yeah, so there's a variety of reasons. One of them is what Steve already described, which is that we are about an ideal distance away from Fermilab, and of course Fermilab already had a proton accelerator to allow us to make those neutrinos that will come here, and so there's that. There was a competition many years ago now to determine where, in fact, this underground science would be located. There were some other very good sites that were considered. There was one in Washington, there was one in Colorado. This site had some benefits. Number one is the geology is excellent for building caverns that are 62 feet wide and 90 feet tall and 475 feet long. Not every rock mass can do that without pretty extreme measures, and this rock mass is excellent for that type of thing. Another consideration is the fact that this site is not competing for use, so it is dedicated to science. For example, I know that Jarrett has worked at a facility in Canada that provides underground science, but it's also an active mine. And so you have to compete, if you will, for use of the shafts and use of the underground space. And so you don't have that issue here in South Dakota. This is dedicated for science. So those are I would say the primary reasons. There were certainly other factors that went into the decision, cost and support from the state, and the fact that we had a philanthropist in this state that was willing to provide a pretty substantial starting fund to get this place going. Those are some other factors.
Good point. Actually, I think there was a question in the back that we haven't. Oh, right here. Sorry. Yep. Let me get that.
Can you help us to understand the commercial applications of the science?
Good question.
So I'll take that. So this is by and large what we call blue skies research, understanding how nature works. it's been our experience over several hundred years that having understood how nature works, the commercial applications then follow from that. There's an example I like to quote. About 150 odd years ago, late in the 19th century, the electron was discovered. And at the time, in fact, there was a comment from one of the scientists to a politician who'd said, "What's it good for?" And he said, "I don't know, but I'm sure you're going to find a way to tax it at some point." And that's the electron. And the electron is what gave us the whole of the 20th century and 21st century microelectronics, your cell phones. Basically, the electron gave us modernity. And so with the neutrino, there are a few applications. I mentioned one earlier, which has to do with reactor monitoring, understanding perhaps someone doesn't want to necessarily have you examining their reactor. You can examine it from a distance with neutrinos. And there are a couple of other things like that. But right now, there really isn't much in the way of neutrino technology. But I like to say I'm working on the technology of the 22nd century. I think the neutrino will be the electron of the 22nd century. And it's hard to predict. No one in Victorian times could have predicted the cell phone. And so it's hard to predict, but it's always reliably the case that when you really are pushing boundaries, understanding nature, eventually from that comes a commercial aspect to it.
One other thing that I'll tack on to the end of that is the development of sensors, looking for some of these rare signals. Sensor technology is often at the forefront. So the basic research and technologies that come from looking for neutrinos and dark matter can have other applications in industry as well. So one other realm that you may have heard of recently, quantum systems, quantum sensors. There are instruments and basic physics experiments using quantum sensors to look for this rare process science, and those may come into more general use in industry as time comes on. That's a very good question. Other questions in the room? Maybe I'll throw one to the audience. Oh, sorry.
Yeah, I'm just curious, where's the funding coming from? Is it private? Is it government? Is it multinational? So if you find something, let's say that supports the national defense industry, do we own it? Is it shared? Like, how does that transpire?
So yeah, that lets me talk a little bit about how international this is, which we haven't really mentioned so far. So the science is being done by, or will be done by a consortium, a collaboration of 1,400 scientists worldwide from 35 different countries. And so they've all come together in the common interest of understanding nature a little better. Now, as Jared said, in the course of doing that, you're pushing technology in a variety of different ways, particularly with sensors and that kind of thing. And so when it comes to patenting technologies, then that might be something that's a little more in the realm of one nation rather than another if they developed it. You know, there's a need to patent, but I would say that this science is incredibly collaborative, and it is so far away from the sort of national security concerns that one might have in other areas of technology that it's almost, I can't honestly think of an example where you would have those sorts of concerns with this sort of experiment.
So specific funding for DUNE, LBNF DUNE, largely Department of Energy, but there are a number of international federal agencies that contribute. So for instance, CERN, the big international lab in Europe, they're playing a big role. They've purchased the combined 15 million pounds of steel that's in Rapid City. Those cryostats were an international contribution. Some of the detector technology, the planes that will measure the interactions that the neutrinos have in the argon are also international contributions. More widely or more broadly, science at SURF is funded. So SURF is funded also through Department of Energy. Some of the science at SURF is funded through the National Science Foundation. And you may have heard in the news that the funding there is being cut. That could impact science coming to our state. NASA funded some early efforts at SURF. Some of the biologists looking for how we would explore life on other planets. They tested a sensor underground, actually on the drill core that was used to characterize the geomechanical properties of the DUNE rock. There was a sensor that went on the 2020 mission to Mars. So basically, we're sending our biologists and geologists to another planet with these instruments, and it was tested underground here. So NASA played a very big role in early science funding at SURF as well. And then for private, you mentioned what role private contributions have made. Of course, for SURF, Sanford Underground Research Facility, T. Denny Sanford was very important in getting the ball rolling for our organization, and really is one of the reasons that we exist. Other large instruments, there are some telescopes, observatories that have recently received some private funding. And so that's emerging. It's not a very strong component right now. And we're very fortunate in the state of South Dakota to have the private, federal, and state. The state of South Dakota over more than a decade has appropriated $75 million to science at SURF. So we're very fortunate to have a strong partnership with both the state, the federal agencies, and Denny Sanford, and hopefully in the future we'll be able to leverage that partnership to get more money in each of those pots.
And Jared, if I can add, about half of the detectors come from international partners. So you mentioned the array of countries, and as I mentioned, they are already producing those detector components and ready to deliver them to us. And then for the cryogenics, we also have substantial contributions from Brazil as well as from Switzerland. And so, and not only is CERN providing the steel for the cryostat, but clearly they did all the design for those vessels, and they are funding the installation activities.
Excellent point.
Off on a different subject, is there a connection between neutrinos and dark matter?
You want to take that?
Oh, sure. At one point, we thought there might be. Steve mentioned that the neutrino is the most abundant particle in the universe. And even if they have a small amount of mass, you have so many of them that maybe they make up the missing mass that we know must exist in some form, and we call it dark matter, based on the rotation speeds of galaxies or gravitational lensing, light bending around objects that we can't see. We now know what do we know? We don't know the mass of the neutrino, but we know that it's lighter than a certain amount, and that low limit that we've placed on the mass of the neutrino disqualifies it from being the majority of the dark matter. We know that the neutrinos have mass, given that they change from one type into another. Quantum mechanically, that process requires mass. We don't know what that mass is, and there are experiments in a race to find that property of the neutrino. The neutrino was invented in the 1930s. It was first seen in the 1950s, and we still don't know how much it weighs, and we still don't know precisely some of its fundamental characteristics, which is why LPNF DUNE, this project, is in existence. It's the planet's most comprehensive next set of measurements for the neutrinos. So right now, we don't believe that the neutrino forms the vast majority of dark matter. Does not. And so we're looking for other particles that we've never seen. WIMPs, weakly interacting massive particles. Maybe the dark matter interacts as strongly as the neutrino. And you heard from Steve earlier how weakly the neutrino interacts. We've seen it, but it's very hard to detect. We haven't seen dark matter yet. We know something is out there based on our observations. We have not seen it, and we're hoping that it interacts as weakly as the neutrino, because then we have a chance of seeing it the same way we've seen the neutrino. Other questions? Right next here.
If Switzerland has their own underground lab, so why do they need you? Why did we?
Switzerland's lab is underground, but it's only relatively shallow. They don't have the shielding that a mile of rock provides. Their accelerator is maybe 300 feet, 100 meters underground, and that's mostly for shielding the radiation that's produced in these intense machines. So they can't do the same science here that we can with the mile deep. It's the deepest laboratory in the United States, one of the deepest in the world, in fact.
But also, it speaks to how this science is done, because a lot of Swiss scientists, a lot of scientists from Brazil, all across Europe, are coming to South Dakota to do their science with DUNE. At the same time, a lot of American scientists go to CERN in Switzerland to do their science. And so it's really, it's an extremely international endeavor. And each facility focuses on what they're best at, given the capabilities of the facility. But they're both worldwide facilities. Everyone comes from all over the world, which is I think a really important aspect of the science that we do. It's very global, very international.
Steve, if I can add, I think, yeah. No, I want to reiterate, I think that's how compelling this science is that is going to happen here. And it's also worth noting, this is the first time CERN has made such a contribution outside of Europe. And so we're very excited for this international partnership and this joint endeavor and the results.
Steve mentioned earlier, almost 1,500 collaborators just on the DUNE experiment itself. That involves over 200 institutions globally and over almost 40 countries, I should say. So that one experiment is extremely global, and science in general is extremely global. The dark matter experiment I mentioned, LZ, although smaller in scale, maybe 200 scientists, not 1,500 scientists, but 35 countries involved there, and that science that's going on at CERF today. Another question.
What are we good at here?
What are we good at here? I guess I can start off and others can chime in. At CERF, we have this great resource in the former Homestake mine, now dedicated to science. It just happens to be in a sort of a magical distance away from Fermilab to do the neutrino studies that the DUNE experiment is performing to search for characteristics of neutrinos. So that's a great attribute. CERF as a facility has a number of unique attributes as well with the geology. There are a dozen rock formations. We've been talking a lot about physics today, but the geologists and biologists come from all around the world, all around from many countries. We had someone from Australia come and look at some of the drill core to understand why the gold deposit happened in the Black Hills. And so that geology and niches for life underground and the access that we provide to that massive rock is very unique. We mentioned that I used to work up at the Sudbury Neutrino Observatory, now SNOLAB. Steve and I were on a project up there with competing interests from the mining company. So the mining company isn't interested in having biologists and geologists roam through their facility. You go to the science lab and you stay in the science lab and you come out on the cages or the elevators they tell you to come out on. We don't let scientists run amok underground and do whatever they want, but there's a lot more access to the environment, to different rock formations, to different areas where life might take form. That is not a shared attribute for other underground labs. We have a workforce that is now got a lot of experience in maintaining clean rooms and supporting the rare process physics type of science that are necessary for detecting neutrinos and dark matter and other rare process events. And just the environment, the state is very supportive. We're considering an expansion to build even additional caverns beyond what you see underground here for LBNF DUNE, because we want to attract the next generation of dark matter and some of the other neutrino experiments. So there's a recognition that science is good for South Dakota, and there's a great partnership with the federal, state, and private that we talked about already. So those are some of the attributes that I think that we're good at, and that's why scientists want to come here. I'll get in the back. There's one right here.
Why did you guys make the cavern? Were the experiments too deadly to do it out in the open or in a container?
Let's find out how deadly it is.
Right. So, yeah, I can take that one. So Stephen kind of tried to describe this a little bit earlier. the depth helps us shield from the cosmic particles. So we go underground to make it so that we can see the neutrinos and not see all the other stuff. It's like you finding a needle in a haystack. Well, get rid of the haystack. It's a lot easier to find the needle. That's what we're doing down here, is getting rid of all that noise. I think Jarrett usually uses the example of imagine yourself in the middle of a football stadium and you're trying to pick out one person, and everybody, the whole stadium is full of people and they're all clapping and cheering, and it's pretty hard to pick out that one person. Now get rid of just about everybody, and maybe you've got 20 people in that stadium, and that one person is yelling at you, and now you can find that person. So that's why we go underground. The hazards of the experiment, the argon is, you're breathing argon right now, as was mentioned. It's used in welding all the time. There's no real hazard from the argon, with the exception of it does displace oxygen. So, and especially when it's in liquid form, when you go from liquid to a gas, it actually expands 800 times its volume or something like that. And so that is something we pay close attention to, is making sure that we've got everything very safely secured, and we got ventilation systems that'll pull that gas away if that were to ever happen. But there's no radiation, for example, here at the far site. At the near site, when they create the neutrino beam, there is some radiation, and they've got some shielding that's involved with that. But that's what they've been doing for, I don't know, 70 years at Fermilab, something like that. And so they know what they're doing. But out here, we don't have any radiological concerns. It's really, you know, the detectors are underground purely to improve the science.
Oh, when this experiment is running, what temperature and pressure will the argon be in the tanks?
So I can take that one also, I guess. You know, the argon is about negative 300 degrees Fahrenheit. We actually cool it. Kind of an interesting side note here is we create liquid nitrogen, which is negative 350 degrees Fahrenheit. We create that liquid nitrogen underground, and then that's what we use to cool the liquid, the argon, into a liquid. And so very cold. The pressure is pretty doggone low, simply because if you let it build any pressure in that detector, the detector is 60 feet wide and 200 feet long, and any appreciable pressure would be very difficult to control with that big of a space. So you know, it's millibars of pressure inside the detector. At the bottom of the detector, it's full of argon. So you've got, you know, argon has got a specific gravity 1.6, I think. My memory is right. So heavier than water. That's one of the benefits of argon. There's more molecules packed into a square foot, square whatever you want. But you know, there is some pressure at the bottom, but there's no real gas pressure.
Yep, very good. Oh, yeah, go for it.
Earlier, you showed a marker on the floor, which was identified as the target. All of this steel and all these other bits, I assume are going to be built on top of that. That's not the actual target, but just a placeholder for where those things go.
So I know I'm hogging the microphone, but I was go ahead.
So, yes, so this target that you see is in the nominally immediate center or exact center of the CUC. So if I were to look this way, to my left, as I'm viewing down the cavern here, Jolie is about 150 feet and 60 feet down. And then there is a twin cavern about 160 feet and 60 feet down on the opposite side where these detectors will be built. So that 60-foot additional depth is just to, you know, to accommodate the height and the sheer volume of the detectors themselves. But the, sorry, you're switching there. The target that you saw there is just where the beam is being aimed. It is not a pinpoint beam It is when it leaves the beam line in Batavia, it's very small, but it grows to a pretty wide size as it travels because just the sheer expansion of the beam without additional focusing magnets during its transit all the way here to South Dakota. By its nature, it expands. So
I'm gonna jump in here because I really was hoping somebody would ask about aiming. Because I think it's an interesting story. So many of you may know Randy Dybert. He is a senator in the state of South Dakota. He's also a surveyor. He was involved in what we believe to be the deepest plumb bob survey in history on Earth, which was down these shafts to determine the exact location of that aim point that Mike was just showing us. And so we know that location relative to Fermilab, plus or minus 6 inches in any direction. And that is a pretty amazing engineering feat to be able to get that survey that far. And something you may not think about is we've got a Yates shaft and we've got a Ross shaft. They're about 1 kilometer apart. And if you put a plumb bob down those two shafts, the bottom is actually closer together than the top, because the center of the Earth is, straight down, but we're on a curve. And 1 kilometer is far enough to make a little bit of difference in that curve. And so that had to be factored in. We did the plumb bob survey down both shafts, and we had to factor in the curvature of the Earth and how that would affect that distance between as we went down. So I'm an engineering geek, so I find that interesting. Hopefully others did too.
So we get Wi-Fi and network underground, but we don't get GPS underground. And so hence the plumb bob and the heroic efforts to do the survey. Other questions?
Kind of building on that engineering aspect. I don't know if people know how many feet or even miles of horizontal cavern we have down there that was mined. Do you have any numbers on total feet, either dug like these were, or existing mine caverns? Do I have any idea how many linear feet and how many tons of material came out during the cavern expansion process?
I know linear feet for the tunnels underground, it's almost 400 miles, 600 kilometers. So the mining company Homestake, over 125 years of mining from the surface down to the 8,000 foot level, that represents 400 miles of tunnels. And these caverns will add a little bit to that because those weren't dug by Homestake, those were freshly excavated. I'll let others comment on the amount of rock that came out just for these caverns, which is very impressive as well.
Yeah, we excavated about a mile, depending on how you measure it. Obviously, there's different size caverns and whatnot. And some of that was existing and we just made it bigger, but about a mile if you took it just walking through distance. We pulled about 800,000 tons of rock out from the underground. And in fact, in the room you're in, if you turn around and look down into the open cut, you can see that pile of rock and you can see how small that volume is relative to what Homestake pulled out back when it was a mining operation. And, the caverns, as we had discussed, they're 60 feet wide, 90 feet tall, 475 feet long each. Where Mike is at is not as tall. It's only about 37 feet tall, but it's actually longer. It's about 620 feet long. So very, very large underground excavations. That 800,000 tons equates to about 300,000 cubic yards. But that was pretty small relative to what Homestake did. And I do want to mention one other thing is, since you're in the visitor center, as you depart there is a model of all of those tunnels, those almost 400 miles of tunnels that Jarrett described. And you can see the caverns that we're in that model, and they don't jump out at you because it is, despite their size, it's a relatively small footprint in the overall size of this facility.
Very good. Yeah, the open cuts, we've drawn the shade in the classroom here, but if you go out and around, there's an observation deck. I believe 300 million tons of rock was excavated just from the open cut, and we're putting in 800,000 tons of rock, and you saw image-wise what that rock represents with the huge caverns that you were seeing images of today. So literally a drop in the bucket, 800,000 tons compared to 300 million tons, less than 1/3% of the volume of just one mined area is the equivalent volume of these caverns. So we're at the bottom of the half hour here, or at the bottom of the hour, so we're going to wrap things up. Some of us will stick around. If there are any other questions, we can take those in the room. But I want to thank you all for attending the morning session here and learning about LBNF DUNE. Thank our presenters. A reminder to pick up a schedule so that you can plan your day and be as efficient as possible. There are events up at Surf, Shangleska Wakan, the homestay tour, or the hoist room tours. Those always fill up quickly, so if you have an interest there and they haven't sold out yet, or ticket-wise, they're free, go check that out. The Opera House has a number of exciting events with our keynote at the end, 4 o'clock, and then also stay tuned here at the Visitor Center for additional events later on today. Thank you once again and enjoy Neutrino Day.